axiomatization of that. So it means that we have the presence of an environment. We are in fact sending this qubit, this quantum system to the environment. So we'll see how we can axiomatize the action of the environment and what are the properties of these quantum operations. And if we combine this new action with what we have seen before, for instance, the notion of classical structures or compact structures and so on, what we obtain is a very powerful graphical language, a framework, where we are able to describe, for instance, measurements. We are also able to describe classical channels. And using these properties, we will be able to describe and improve properties about protocols. Okay, so this is basically the idea. Okay, so before the description of this action, the trace out, let me briefly go back to the description of all the context, all the tools of the structures that you already know about. And first of all, the dagger symmetric monoidal category. So here, as I said before, the time is going up, contrary to Ross's talk where the time is going down. So it's optimistic to say that time is going up. And so we are representing a morphism like this, using this box, which is not symmetric, it's important. So we have a composition, F followed by G, so it's like this. We have a tensor product, so meaning that we have two systems, by F on one system, G on the other one, which is just like this. We have the dagger, which consists in representing the box upside down. And I'm not going to describe all the rules, all the rules for this, because you have heard about this morning, and I have no nice animations, so I just give this one as an example. If you take the dagger of the composition, you obtain this. Okay, it's the way around. This refers to the nice presentation, nice animations by Ross, if you want to have more details about the rules behind this dagger symmetric monoidal category. So this is the framework. So one of the first structure which has been pointed out is the compact structure. So basically this kind of morphism. So it's morphism from nothing to two things. So let's say two qubits. So in fact it's a quantum. We can interpret it as a quantum state, two qubit quantum state, which is an unstable state. Okay. Basic interpretation of this is Napier state. So this is a compact structure, so it means that it satisfies the following conditions. So here we have this morphism, this unstable state. We take the dagger of this, so we just write it upside down. Okay, so if you take this. And so if you compose them together, you obtain the identity. And here, if you take this state and you apply the symmetry, it's the same as before. So it means that this is a symmetric unstable state in the interpretation. So somehow here you can recognize the teleportation. I will talk about the teleportation later on in more details. So this was the compact structure. Now the classical structures. So we say that we have a classical structure if we have a family of such morphisms with any number of inputs, any number of outputs, which satisfies the following composition rule. If you compose them, you compose two of these morphisms like this, with some common inputs outputs here, then you just, according to the spider theorem, you just count the number of inputs, count the number of outputs, and put the dot in the middle. Okay, so we have here a very simple composition rule. There is another rule which is missing, which is that if you have in that case, this is the copy. Okay, so this is the, for instance, the copy in the standard basis. Okay, and okay, so here it's a copy, it's not cloning. Okay, it does not violate the no cloning theorem. And for instance, if we apply this copy to this state, the state that we obtain is just by linearity 0, 0, 4, 0, 1, 1, 4, 1. So we obtain 0, 0 plus 1, 1 over square root of 2, which is clearly not two copies of the plus state. And in fact, it's not surprising that if we are composing plus with this copy, we are obtaining this state because this is this condition. Okay? If we take the state plus and we apply the copy, then according to the spider, it's just one dot with two outputs. So this is this one, and here we have the condition that this one is equal to this one. That is, it's an alternate state. Okay. Okay. Is there an equation? Okay, so you have seen that several times. Okay, so next step. So this is not the cloning, this is the copy. So it means that some states we cannot duplicate all the states. However, we can duplicate some of them. Okay? Basically, the idea is that the basis states are duplicated. If we put 0 or 1 here, we obtain two copies of it. So for a given classical structure, the elements which are duplicated by these classical structures are called classical elements. Okay? Classical element is an element which is duplicated by the classical structure. We are introducing the morphism. So it's the interpretation will be just the Hadamard gate. So what are the axioms that we ask? So we say that if we have here an alternate state that we are applying Hadamard on one side, on this side, is the same as applying it on the other side. We ask that H squared is the identity. And we have also this equation, which is very important. This is the off law. This is if you apply the copy, then apply H on both copies, and then the co-copy multiplication. Then here you obtain this. That is, there is no connection between this and this. Okay, so this off law will keep this one on the blackboard because we will use it several times. Okay, so here the idea is that we have the classical structures, and instead of considering several classical structures which are unbound and using two colors for them, green and dot, as we have seen this morning, we prefer to use just one color and introduce this gate H, which is allowing this basis change, to change the basis. However, what I'm presenting here is not equivalent to the complementary basis because we have the off-flow, but we don't have the bi-algebra equation. Okay? With the complementary basis, we have this equation. Okay. If we have complementary basis, we have this equation. Okay. Here we are not asking for this one. Here it's a weaker version where we are asking for the outflow, but we are not asking for this one. Okay, so this is the context. This is what we are going to use. And now we are ready to talk about this trace out. So, We have seen all these structures inside, so the compact structures, the basic structures, the classical structures. And now the idea is that in order to be able to talk about this, the environment, the trace out, we consider a larger category, which is providing this environment. Okay? And so basically we say that an environment for a Dagger compact category C pure, so we take this category, the environment is a larger category, such that C pure is a sub-Dagger compact category, such that for any, so the object of these larger categories are exactly the same as the objects in C pure, and for every object we assume that there is such a morphism from A to I, so which consists in tracing out the system A. So we have the following conditions. So this one consists in saying that if you want to trace out two systems, you can just trace out the first system and then trace out the second system. It's not very hard. Here, this one is interesting, that is, if you have an unstable state, this is the usual interpretation of this compact structure, and if you trace out one of the qubits, what you obtain is a maximally mixed state, which is represented by this. Okay, so this is representing the maximally mixed state. We take the quantum state from the environment. We don't know anything about this state. This is a maximally mixed state. Okay, the interesting action is this one. So this is, I have no simple interpretation for this one, this axiom, but it turns out that this is a very powerful axiom. It says that if you take any F and G in this C pure, in this category C pure, then you have this equation. You have F followed by F dagger equal to G followed by G dagger, if and only if F followed by trace out. So if you apply F, and then you trace out the result, is the same as applying G and then tracing out the result. Okay. So we assume that we have this axiom. Okay, so first, an example of such environment category. This is the category of completely positive maps. So the morphisms are the completely positive maps. So the objects are the Hilbert spaces of dimension n times n. So intuitively the density matrices. So this is the category, the environment category, and the subcategory here, the pure part, is composed of the morphisms which are of that form, that is, which are composed such that the Krauss decomposition of the completely positive map is just composed of one element, or in other words, it's composed of the completely positive map which are not producing classical outcomes. Or in other words, the completely positive maps representing the evolution of a closed system. Okay, so this is the pure part of this environment category. And the trace out is nothing but the trace. Okay, for a given matrix, density matrix, this is the trace of the matrix. So it turns out that we satisfy the axioms, and the main thing to prove is this one. So in this case, this axiom is satisfied. So here, this is the proof. So this is some linear algebra. I'm not going to the detail, but yeah, you can check it. It's satisfied in that case. Okay. Okay, so we have this. So what are the interpretation of the compact structures, the classical structures that we have seen before in this category? So in fact, everything is working very well. So the interpretation of this, so the usual interpretation of this is just the state K plus. So here we're working with density matrices, so it's the corresponding density matrix. Here, this is the usual interpretation for this is the integral state, the EPR state. So here it's just the density matrix corresponding to this state. So as I said before, we interpret this as the trace out of the qubit. Here, this is the maximally mixed state. This box is just Hadamard. Okay, with my Hadamard, it's so we have this if and only if f followed by the trace out is equal to g followed by the trace out. Okay, so in that case, f is an isometric, so it means that f followed by f dagger is just the identity. This is the definition of the isometry. So here we have this where g is the identity. This is a special case. So if we replace here g by the identity, it will be this. Okay, so it's just a direct application of the axiom where g is the identity. Okay, so now combining this trace out with the copy, we obtain what we call a classical channel. If we have one input, we apply the copy, so we obtain two copies of this input, and we trace out from this copy. And we obtain something with one input, one output, and we call it the classical channel. So the first property of the classical channel is that the classical channel is idempotent. So if I compose two classical channels, I obtain a classical channel. Okay. So the proof is here. So we want to prove this. So in fact, we are going to use the axiom. Okay? This is the only way to get rid of this trace out. So notice that in the axiom for f and g here there is no outputs. Okay? There are just inputs. So first of all, we use the compactness in order to turn all the outputs into inputs. Okay. Since we have the compactness, we can do it. So now we have this, and we are applying just this axiom where f is this morphism and g is this one. So it's just the application of the axiom. And now these two are equal because according to the spider, both of them are equal to this. Just count the number of inputs, the number of outputs, since they have the same number of inputs and outputs. They are the same. Okay. So this is the proof that of the idempotency of the classical channel. Okay. Okay. What's next? So we have defined classical elements. So in fact, it turns out that classical elements are just transmitted by classical channel. You have a classical element, you have a classical channel. If you send this classical element through the classical channel, this element is just transmitted. So here we ask for an additional assumption on the classical element, which is that this classical element is normalized. So it means that we have this. So here there is no typo, here it's empty. Okay. So here empty means that this is the identity on I. So in the interpretation, it's just a complex number of 1. Okay. So here it means that if you take this classical element and apply the trace out, if you obtain 1, then the classical element is normalized. So up to this additional assumption, we have this, that is, the classical element is transmitted by the classical channel. The proof is clear. So we know that the classical element is duplicated by the copy. So we obtain this. And thanks to this normalization condition, we get rid of this part. Okay, so we just obtain the classical element. Okay, what's next? So now, if we compose two classical channels, but in between we add an H morphism, we apply H between the two classical channels. In that case, we obtain a noisy channel. In fact, we are completely illustrates the draw of the fact that if you take an entangled state and trace out a copy, you obtain a maximally unique state. Here, it's the same idea, but the other way around. Okay. So we have this, and starting from this, if we apply the axiom, then we obtain exactly this equation. And now, if you apply the spider, you can rewrite this part as this one, okay, just by merging these two dots here and these two here. So we obtain this, and thanks to the upflow here, so this one is equal to just disconnect thing. Okay, we can remove these two parallel edge, obtaining just these two things. Okay, so this is the proof that if we put an edge in the middle of the classical channel, then we obtain a noisy channel. So it means that we cannot transmit any information using this channel. Okay, so now if we have a classical channel and if we try to send something which is unbiased with a classical element. Okay, we take a classical element and we obtain H, we apply H. So basically we take a zero state, apply H, so we obtain plus, and we want to send this plus through the classical channel. What's happening? In fact, the state we obtain is just a maximum unique state. Okay. With a classical channel, we can transmit classical information, but if we take an element which is unbiased with this classical element, then this element will not be transmitted. So the proof is as follows. So the first step uses the fact that the classical information is transmitted. This is the element that we have seen before. First step is just okay. We know that the classical element is transmitted by the classical channel. So we use this is the first step. And then here we recognize the previous case. These two classical channels with H in between. So this is a noisy channel. And here, thanks to the normalization condition, we just obtain this maximum unique state. Okay, so we cannot transmit the unbiased data through this classical channel. Okay, so that's it for the classical channels. Now, it turns out that using this trace out, we can also represent a measurement. So how to do it? We do it in the following way. So we say that in order to do this measurement, in order to implement this measurement, first we apply the copy. Okay, copy the state. And now we take one of the two copies and we make it classical. Okay, we send this copy through a classical channel. And we obtain the classical output. Okay, so we interpret this morphism as a measurement where the quantum input is here, the quantum output is here, and here this is the classical output. So I don't have this, but we can verify that if we apply the measurement twice, then we obtain the same outcome. So let's take the measurement. Okay, so here we have qubit, we apply the measurement, we obtain the classical outcome. If we measure again the same qubit, apply the measurement twice. So it's the same as just apply the measurement once. And then make two copies of the classical outcome. Okay. So it means that the state, the quantum state, so if we apply the measurement twice, the quantum state is the same as if we apply the measurement just once. And here we have two classical outcomes, and these two classical outcomes are the same because it's just a copy of the same classical outcome. Okay. So using this axiom in particular, we can prove this property. So this is the more general case of the measurements, but we can also consider destructive measurements. So destructive measurements is when there is no quantum output. Okay, just get rid of the but in the graphical language it's the same. There is no problem with this. Okay, what's next? We can, so since now we have classical channels, we have measurements, and especially we have classical data, we can talk about controlled unitary. So a controlled unitary, the idea of the controlled unitary is that in fact we have a family of unitaries, a family of maps, so Ui, which are indexed by I in some set S. Okay? And we say that this is a controlled unitary if for any I in S, this is a unitary, Ui is unitary, means that Ui is equal to the identity, and this is this. Okay? For any I, we have that Ui is a unitary. Okay? This is what we mean by controlled unitary. So here, I in S is the classical input. It's classical. This is classical input. And we say that this is representing such a set of unitaries, that is the classically controlled unitaries, if the following axioms, following equations are satisfied. So corresponding to this one. Okay. So first, if we apply for any I, for any classical input, if we apply F with this input I, followed by F dagger with the same input, with the same classical input I, then we obtain the identity. And here it's the same but for F dagger. So it's the definition of an abstract classically controlled unitary. So an example of such controlled unitary is this one, which is in the interpretation that we have, it's nothing but a Z correction. But is here we have an input, let's say 0 or 1. If the input is 0, then we do nothing. If the input is 1, then we apply Z. Okay. And to prove abstractly that this is a controlled unitary, we can prove this. In fact, in that particular case, these two cases are the same. And it's just this one. So here we apply again the spider, obtain this, and this is again the upflow here, which allows us to go from here to here. So we have an instance in the use of the upflow. Okay, so we can define lots of transformations. So for instance, the C0 is follows. So this is the usual way to define it. So here in the middle, we have seen that this is a control Z. So if we apply H before and after, we can control not. Here it's a bell measurement. So how to perform a bell measurement? So a bell measurement, just apply C0, then H on the control qubit, followed by measurement in the standard basis. Okay, this is one way to implement the bell measurement, and this is exactly what we are doing here. So here it's the C0, here it's H, and then followed by the 1 qubit measurements in the standard basis. So for the bell measurement, we can do something similar to this one. That is, if we apply the bell measurement twice, then we obtain the same as applying it just once. Okay, so we can define all of this, and it turns out that in the interpretation in the completely positive map, this is what we are expecting. And so now we are ready to talk about protocols. And the first protocol that we are considering is the teleportation. So here it's the description of the teleportation in an informal language. Okay, it's just a graphical description, informal description of the teleportation. So we have the bed state, initial entanglement, which is shared between Alice and Bob. Alice on that side, Bob on this side. Alice is having another qubit in an unknown state. She is applying a bell measurement. This bell measurement is producing two classical outcomes, so we're representing the classical outcomes in blue. Okay. And so she's sending these classical outcomes to Bob, and Bob is applying some corrections, X or Z, depending on the classical outcomes. So this is the full representation of the teleportation. Notice that here it's not a post-selected version of the teleportation. Okay, it's not the case this protocol here. So the base state is just this wire here. The bed measurement, we have seen what is the bed measurement before, it's this. And here the classically controlled operation. So for Z, we have seen that this is this part with the classical, with the trace out here. Okay, it's this part for the control Z, and for the control X, we just have H before and after. Okay, so from what we have seen before, we can translate, we can represent the teleportation in our language like this. And here we see that we have a clear distinction. Here we have the classical channels. Okay, here because of this trace out here, here we have two classical channels. Okay. Can distinguish classical channels and quantum channels. And we want to prove that this is the identity. Okay, this is the teleportation. So we can represent the teleportation, and we can also prove that this is the teleportation. Here is the proof. So the proof is not so big. So what is the idea? So here, first step, here we see that we have two H on the same wire, so we can just remove them. Okay, because H squared is the identity. So we are now here. Now we can apply the spider for these two dots which are connected, like here. So we can merge them. We obtain this. Okay, so if we merge this dot and this one, we obtain this. Now we use our favorite flow. And from here to here, we can remove these two H's because they are applied in parallel. We obtain this. And now we are doing something very similar in that case. We have two H's. We can remove them. And then we have two dots. So we can merge them, obtaining this. And again, we can remove the two H's because they are in parallel, obtaining this. Okay, so this is the identity. So this is the teleportation. Then up to some normalization condition, we can remove these two scalars. Okay, so this is the proof of the teleportation. Here it's interesting to see that we have these two scalars here, because if we take the teleportation now, if we slightly modify the teleportation by keeping a copy of the classical bits which are sent during the teleportation. Okay, imagine that here we take a copy of this bit and a copy of this bit. We can add it to the diagram, this representation. And if we do that, we'll see that at the end of the day, here we have two wires. Okay? The two copies of the bits are these two wires. And so, and using this idea, we can prove that the classical bits which are sent during the teleportations are just random bits. Okay? There is no correlation between the bits which are sent during the teleportation and the state which is teleported. Another example is the dense coding. So it's kind of dual example. So now we have the classical inputs, two classical inputs, two bits of information. We have a base state which is shared between Alice and Bob. Alice is encoding this same basis, Z, then the BB84, so it turns out that this pi is able to know what is the bit which is transmitted from Alice to Bob. So and it turns out that this particular case can be represented as follows in the graphical language. So this is the encoding in standard basis. Here this is the Z measurement, where Alice is keeping one copy of the outcome. She's sending the quantum outcome to Bob, and Bob is applying the measurement in order to obtain a classical outcome. And it turns out that we can rewrite this just as this, which means that we have a classical channel, and the information which is sent by Alice is just copied, and Bob and Eve have the same classical data. Okay, so in that case, Eve has the same data as Bob. So in that case, where Eve is using the other basis for the measurement, this is very similar, but there are two H's here, and because of the H's, and so here we can see that we have a classical channel, H, and also classical channel. We have seen that this is equivalent to a noisy channel. So at the end of the day, we'll take this, that is, it's a completely noisy channel, that is the qubit, which is sent by Alice, it's just trace out, and the two qubits and the two bits that Eve and Bob are adding are just random bits. So this is just two particular cases of the BB84. Okay, so that's it.
Do we have any questions? actually an equivalent representation where what's here classical is represented by a single wire and what's quantum by a double wire. So there's kind of an equivalent way of doing the same, and then you really see two different kind of wires, but they're still sort of constructed on the same object.
Just continuing the same comment, so I thought you set this up deliberately this way so that there is an ambiguity between what's classical and what's quantum. The idea is that you want to sometimes encode classical information in a quantum state. Is that right?
Yes.
And so it would be quite this ambiguity that you have here is what you want by design. That's right?
Yes.
I was wondering, when you proved the noisy channel, you went from a diagram that had interactions with the environment from a diagram that didn't have interactions with the environment. And I was wondering, how did you do that? Because
This one?
yeah, for example, you went from the first diagram having two interactions with the environment to a second diagram having no interaction with the environment. I was wondering, what action did you use?
So there is just one way to remove this trace out is to use this action. Okay. So we take this one, and so we want to use this action. So the first thing to do is to turn the outputs into inputs, okay, because here there is no outputs.
Okay.